The next problem is called climbing stairs. We are basically climbing a staircase, and it takes n steps to reach the top, and n is basically given to us as an input to the function. Each time we can either climb 1 or 2 steps. The question is, how many distinct ways can we climb to the top? So, for example, here we have n equal to 2, and basically, if we have to climb 2 stairs, then we can either do it by climbing first the first stair and then climbing the second stair. This will equal to 2. So that's our first way of how we can climb 2 stairs. The second one, because we can jump kinda to the second stair by taking 2 steps, it's just basically to take the 2 steps, this option. And in that case, we'll have our second way. So the number of ways that we can reach the n equal to 2 steps is basically 2. So we return that as the output of the function. Now for n equal to 3, we will have the following combination. So we can basically take 1 step, then again 1 step, and then again 1 step to reach the third stair. The other option is to take first 1 stair and then jump to the third stair by using the 2 steps basically. Then we can also do it vice versa. So we can basically jump to the second stair, and then we are only missing 1 stair, so we can just take 1 step to it. So basically, we have 3 different ways, 3 distinct ways how to reach n equal 3. So 3 steps. Also, you can note here that the sequence of the steps also matters. So taking 1 step, and then taking 2 steps is different than taking 2 steps, jumping basically to the second stair, and then taking 1 step. So these are the 2 different ways, and they are counted towards the total number of distinct ways. Now, this problem will be solved using the dynamic programming approach, and this will be the first problem in the dynamic programming category of problems that we will be solving. So for this problem, we'll basically break it down from the recursion to the optimized version using the dynamic programming approach. And to do that, we will go through the framework that I've been using to solve all of the dynamic programming problems. But before we go to breaking down the problems, here are some few important information about how to solve dynamic programming using the framework. So first thing is that how do we know that this is like a dynamic programming problem? So basically, if you have a complex problem, and if that problem can be broken down into sub-problems that can be optimally solved, and there is a relation between the sub-problem and the big problem, basically, then you have a dynamic programming problem. So let's just give an example here. So if we have a problem that calculates the number of distinct ways how to climb n stairs, and we know that we can take only 1 or 2 steps, then basically, if n is equal to 5, we have to calculate the number of distinct ways how to achieve n equal 4 and n equal 3, because those are the last stairs that we will reach before reaching the 5th step. So if we can take only 1 and 2 steps, the last stair, if you're taking only 1 step, will be 4. And the last stair that we will have, if you are taking 2 steps, will be the stair numbered by with the number 3. So in this case, we have now 2 sub-problems that are connected to the major, to the big problem, to the initial problem that we are trying to solve. So we can break down the initial problem into sub-problems and then optimally solve these ones. And there is a concrete relation. So basically, this is called dynamic program recurrence. Basically, describing a problem into a composite of sub-problems that we can optimally solve. Now, how do we know that the ways that we can reach n equal 4 will be different than the ways that we can reach the third stair? We know because whatever we have here for the n equal 4, any kind of combination 2 2 1 1 1 and then like 4 1 4 ones, for example, they will differ than the ways we have here, because in the last step we will take one step here because we are at the fourth stair. So basically, to achieve fifth stair, we can take only one step. And here, whatever we have, we will combine it by 2. So basically, they will differ in the last step, and they will, once added up, they will basically represent the number of different ways, distinct ways that we can reach n equal 5. So this is how we know that we have a dynamic programming problem. Now, to solve dynamic programming problems, basically we have a framework of 6 steps. The first, once we have identified that we are or we have a hint like that we are dealing with dynamic programming problem, we will go through each of the steps first, like explicitly, but then like mentally while we are answering the different questions in this dynamic programming category. So the 6 steps that make up the framework for solving dynamic programming problems consist of first, category. So basically we have 5 different categories that we will go over just in a second. Then we have states. So basically we will have to define the states that we will use while calculating the sub-problems. So there are some information that we have to remember while we are solving the sub-problems, so we can use those information to solve the bigger initial problem. Then we have decisions. So in this case, we have a simple decision either to take 1 step or 2 steps. So basically, we have 2 decisions. Then the base cases are, this is basically coming from the recursion. The base cases are basically the steps that we already know, the states that we have already know the value for. So kind of like we don't have to calculate it using dynamic programming approach. We already know that the corresponding value. So in this case, we know that for the 2 stairs, we can basically have 2 distinct ways of climbing those stairs up. So we can have 1 and 1, and then only two steps. So this is a base case. An additional base case is if you have 1 stair, then we have only 1 distinct way of reaching it by just using the 1 step, by just doing 1 step. So these are our 2 base cases that will help us to solve other sub-problems and finally the initial problem. So for example, we can use 2 and 1 to solve the ways to climb of 3. Because the base of climb of 3 is connected to 3 minus 2 and 3 minus 1. So, and basically these correspond to these 2 ways to climb sub-problems. So in this case, we will have 3 minus 1, we'll basically have 2, and we'll have 3 minus 2, we'll have here 1. So we have to have the solutions for two stairs and only 1 stair, which are basically our base cases. Now, basically after we have declared that, we can code up the recursion solution almost always by using just states, categories, and base cases. After that, we will basically get some time and space complexity, and in most of cases it won't be optimal. So we will try to reduce both of them. That's the best thing. But if we cannot optimize one of them, we will try to optimize the other, at least one, basically. Now, when we move to the categories, and we will solve many problems from each of these categories. But because this is the first step, let's see what this problem, to which category this problem belongs to. So 0-1 knapsack is basically a problem of having different items with different weights and different values. And we are given the weight limit of our knapsack, and we want to maximize the value. So if we pick, basically we are a thief and we are trying to steal as many as valuable items while keeping the boundary of the weight. So the weight of the maximum weight that the knapsack can hold. So in this problem, that's basically it's not our category. The knapsack is the same, but in this case, it's not only 0 and 1. It's not only like don't take the item or take the item. We can have multiple copies of the item. It's basically unbounded. So if there is one item that's light but it's more valuable, we will basically pick as many items of that type as we can to maximize the value that we can generate. Now, the shortest is a critical path. This is probably one of the most important categories for finding, for example, shortest path in graph or a grid. But in our case, this is not something that we need here. The same goes for the longest common substring or subsequence. In this case, we don't have to find a substring or subsequence that maximizes some property. We have to find the number of distinct ways for some number of stairs. And if you see here, the number of stairs for any number is dependent only on the two last values before that number. So if you have 5, we are dependent on 4 and 3. And the Fibonacci sequence is basically just that. We can calculate the next number in the Fibonacci sequence if we add up the previous two numbers. So if we have, for example, 3 and 5 as the Fibonacci numbers, then the next number will be 8 because we are adding up 3 and 5. So our problem belongs to the Fibonacci sequence category. Now, because we know now the category. We know the states basically for the recursion. We don't really we just need the previous two steps. We don't really need the implicit information. We don't have to hold an array of something so we can calculate the initial problem. We just need the calculation for the two previous sub problems. So for example, for 5 we will need the recursion solution for 4 and 3. Now, in the base case, we have basically for 2 and 1. So those are our base cases. That basically leads us to the recursion. So if we have calculated the distinct ways how can we reach the 4 stairs and distinct ways how we can reach 3 stairs, then by using recursion, we can also calculate the distinct ways that we can reach 5 stairs. So basically, we will have our base case. So if n is smaller or equal than 2, then we'll just return the n. This is correct because for 2, we have 2 distinct ways. For 1, we have 1 distinct way. And for 0, we cannot take like a 1 step or 2 steps to reach 0 stairs. This doesn't make sense. So we'll just return n in that case. Now, the recursive relation is basically this relation here. We'll just calculate n minus 1 and then minus n minus 2 to calculate the initial problem, and then we will add up those numbers that we get from n minus 1 and n minus 2 recursively to get the number of distinct ways that we can use to reach n stairs. Now, if we drew a recursion tree, so let's say we have 5 as the number of stairs that we want to reach, we will basically have to calculate 4, and then we will have to calculate 3. But in this case now, for 4, we will basically have 3 again and 2. And here we will have 2 and 1. And again here we will have basically 2 and 1. So as you can see here, we basically have repetitive calculations. So we are calculating the computation for 3. We are calculating again 3 here, and then we have many 2's here. And then basically we'll have 1's again here. We'll have 4 1's that we have to calculate the function for. So we will follow the same path several times, basically increasing our time and space complexity. So in this case, the space complexity is basically just the recursion stack. So in our case, it will be n, because we can have we will basically just decrement by 1. So we each level of the recursion tree until we reach 0. So in that case, we will have the recursion stack proportional to n. Now for the time complexity, because for each step we have, and there are n steps, that's basically the depth of our recursion, we have 2 decisions. So we will have 2 to the n time complexity, which for larger numbers, basically this algorithm becomes useless. So we will have to kind of do the 6th step. We will have to optimize our time and space complexity. Now for this approach is basically called top down approach. Because we start with the initial problem and then we basically break it down, and then the real calculation is happening in the leaves of the recurrent tree, and then we are propagating it up until we reach the initial problem and solve it, because we have already calculated each of the subtrees that computation is the root of, considering the recurrent tree. So to basically optimize this, we already identified the bottleneck is that we are repeating the calculations. We are repeating the 3's here, the 2's here, and 1's here. So for us to optimize it, we will basically have to move kind of the time complexity effort to the space complexity, which basically means that we will use some kind of data structure to remember the calculations. In the dynamic programming world or the computer science world, this is called memoization. So basically, we will hash any calculations that we need in the future. So if we need, for example, 3 again, we will not calculate it again. We only calculate it once, and we will retrieve it from our hash map. So in our case, we'll basically declare memo, which is just the hash map, and it will just store the number of distinct ways for n steps. So in this case, we have the base cases 1 and 1 and 2 and 2. So which basically means for 2 stairs, we have 2 distinct ways to reach them. And for 1 stair, we have only 1 distinct way to reach it. And then we will calculate it by using the climb stairs. We will do the same recursion approach, but in this case, we will, before calling the recursion, we will check if we have already calculated, if we already run recursion for certain n steps. So if we calculate it for n equal 3, we will not calculate it again. We will just retrieve it from our hash. And we will not go down into the recursion. So that basically means that this subtree will not exist, because we have calculated here. This will reduce our time and space complexity to linear, basically to linear complexity proportional to the n stairs, because the recursion stack will be n, that's the total depth, and also that will also be the space needed for the hash map, and the number of stairs that we will calculate on the recursion for is basically n. We can do 1, 2, 3, 4, and 5 if n is equal to 5. So those are the steps that will be calculated and calculating the climb stairs function for. So it doesn't make sense to do it for 6, for example, because 6 is larger than the number of stairs given to us as the original problem. So it doesn't make sense to go any higher. Now we can see if we can make this kind of even better, like if we can optimize it in a different way. But basically, this is it when it comes to recursion, to a top-down approach. The next step in the framework is basically to transform the top-down approach to the bottom-up approach. So in the bottom-up approach, also called the tabulization, so we start with the leaf nodes, with our base cases, basically. And then gradually we build up, we solve basically more complex problems. So in our case, that basically means if we have an array, which we'll call DP, and it's basically kind of the same as we had in the top-down approach, we called it memo. We know that for the base cases 1 and 2, we will have 2 and 1 distinct ways to reach it. So the next stair, the number of stairs that we have to calculate is 3, n equal to 3. And this depends, the number of stairs, when the number of stairs equal to 3, it depends on 2 and 1. And we have already calculated that. We already have it inside of our array. So we'll start our calculation. And in topolization, it's always like multiple for loop. Basically, that's always a thing. In this case, we have like a one-dimensional array, so we'll have only one for loop, and for each number of stairs, so I is basically declaring the number of stairs that we are calculating the distinct ways for. So in this case, we are starting with 3, so we'll be calculating first for 3. We will use 3 minus 1, which is 2. We have already calculated that because that's our base case, and we will do 3 minus 2, which is 1. So in this case, we'll just have 2 plus 1, which is equal to 3. And we have already calculated the number of distinct ways for n equal to 3. And we will basically go and solve this for 4, 5, 6, and so on until we reach n. And then after we have reached n, that's our initial problem, we will just return the value that we have stored in the array. We basically come to the same time and space complexity for this problem. It's linear because we have this dp that's of size n, and also we have a 1 for loop that just iterates over the numbers up until n. So we have linear time complexity. Now, the final optimization that we can do is that we can note that we only need 2 previous values. We don't need the whole array. And this is always something that you can ask yourself. So after you have solved the problem with tabulation, do you really need all of the information that you have used? So in this case, if I'm calculating if I is equal to 6, for example, so here, do I really need the dp of 2? No, I don't need it. I only need the dp of 4 and 5, so only 2 previous values. So we will use this information to basically just declare the 2 helper variables, the 2 steps behind, and this 1 step behind. So basically in this case, step behind. So, and we will start again from 3. So we know that the step behind is basically 2 in the initial, after we trigger the calculation for the first time. Because that's 3 minus 1 basically, so that's the one step behind, so that's the stair 2, and there are 2 distinct ways, and 2 steps behind is 1 because 3 minus 2 is 1, and there's only one distinct way to reach one stair. And we'll kind of do the same calculation that we have done here. So for the current total, we will just add up the 2 steps behind and the step behind. And now for the next calculation, we basically have to reset the values for the 2 variables that we are using. So in this case, the 2 steps behind will become step behind. So for I equal 4, we need basically 2 and 3. And before we had basically we had stairs corresponding to 1 stair and only and the one corresponding to 2 stairs. So what we'll do with the 2 steps behind will now become 1 to 2. So we'll basically do this. And the value that's stored in the step behind corresponds to the two stairs basically. And then we have to switch 2 to 3 because for 4, this is 1 step behind. And what is the number of distinct ways that we can reach 3? Basically, this is the calculation that we have just calculated. So we will set the step behind to the current total from this iteration. And we will continue this as long and up until we reach n. After we have reached n, that means that we have computed the original problem. So in this case, we will just return the step behind, because in the last iteration, we will set it with the current total that corresponds to n stairs. So step behind will hold the number of distinct ways for to reach n stairs. In this case, we only have 1 for loop, so we'll have linear time complexity, but we are not creating any additional data structure, no array, no hash map. We are just using 2 simple int helper variables. So basically, our space complexity is reduced to 1. So we came from 2 to the n and n for the space complexity to basically linear time complexity and constant space complexity. And this can be achieved for most of the direct program problems using this kind of like a little minor framework and following these 6 steps. In the next problems, we will basically get familiarized with other categories in the other categories that we have, and we'll try to approach it using the same framework as we did here.